Okay. So we have representation theorem in theorem 11.1.1 in section 1, right? Oh no, 0.1.2. I'm sorry, as well as the theorem 11.4.8 about uniform convergence, as well as the absolute convergence, right, in this section. Right. So with both theorems, we can write down the representation theorem for Fourier cosine series as well as Fourier sine series. So the first color is about the representation theorem of Fourier cosine series. Right. So the premise is that we let f to be piecewise continuous on 0 to pi. Okay, just half of the period, and have a piecewise continuous derivative on 0 to pi. All right, so to establish Fourier cosine series expansion for such an f, and we actually do the following. So we know, okay, let me write it here. Okay, so originally we have say okay, quite strange function. Okay, so so this function f, okay, has 3 discontinuity at 0 and 1 point in between 0 and pi and at pi, right? So such a one. Now to have a cosine, Fourier cosine series expansion, then we first construct an even function. Okay, so the construction is like here. Right, so here minus pi. Okay, and we just do the flipping. So okay, and do here. Okay, and okay, so f of is defined to be when okay, and f of minus x for 0. So we construct an even function like this. Now, f is piecewise continuous, so f sub e is also piecewise continuous. And since f is have a piecewise continuous derivative, okay, you can see that. Then by the symmetry, you know that f sub e also piecewise has a piecewise continuous derivative. Okay, so okay, and so that by theorem 11.1.2, the Fourier cosine, because that is even function, so the sine part has zero coefficients. So the Fourier cosine series is the trigonometric Fourier series generated by f sub e. Okay, f sub e. And so this series will converge to the in this interval, okay, in the open interval here we have goes to the average of the right limit and the left hand limit. Okay, so that is basically in this open interval the conclusion is from theorem 11.1.2. Now, how about the endpoint? To the endpoint, so we see that because of that, so by the way, so you can see we have, so if we repeat the figure for every other period, so we have, say here, okay, and look at the point that the left hand limit and right hand limit will be the same, right? Will be the same at this point. Similarly, the left limit and right hand limit is the same at 0. Okay, and so if we look at the f sub e, because both of them are the same. So when you take the half, then that would be equal to, for example, in here at 0, that would be the right hand limit of original function f at 0. Okay, so it's here. And at pi, then the Fourier cosine series will converge to the left hand limit at x equal to pi. Okay, so it's very clear from this diagram to know that the convergence result at both endpoints. Okay, right. So these two parts also consequences of theorem 11.1.2. Any questions? So you can write the Fourier cosine series, right, generated by, so this would be the trigonometric Fourier series. The same, right? Generated by f of e on what? On minus pi to pi. Okay? Will converge to 1/2 of f e x plus, okay, at each point for x in what? In here. period. So what is that? The green part is just the statement of theorem 11.1.2 for this even function. This even function is a periodic function. Okay, and so for now, go to the white part. When x is in this open interval, then f of x is equal to f sub e of x, right? They are equal because x is in between 0 and pi, not including the both endpoint. Okay, so they have the same. So in that case, we have the conclusion here, right? Because f of e is equal to f of e x minus equal to f of x minus, and f of e of x plus is equal to f of x plus when x is in this open interval. But at the endpoint, for example, at the zero, so at the zero, so now at the zero, so to at endpoint, which must be 1/2 of fe 0 minus plus fe 0 plus. Okay, is that okay? But both of them are equal to the right-hand limit of f at 0. So this is f of plus, the same. Okay? So this is equal to f of 0 plus. Now how about here? That would be 1/2 fe pi minus plus fe pi plus. But both of the left-hand limits and right-hand limits of f sub e are equal to f of the left-hand limit of f at x equal to pi. So this is equal to, okay. Now the second statement is from what? From theorem 11.4.8. Okay, so if we find AB, so that A greater than or equal to 0, B less than or equal to pi. So basically, we find a finite cost interval such that f is continuous. If f is continuous in this interval, then f of f sub e is also continuous. Okay, f sub e is also continuous, and then so the second statement is from theorem 11.4.8. Any questions? All right, no question, good. Now the second corollary is about representation. Theorem of Fourier sine series. Okay, so the f again same, piecewise continuous on 0 pi, and has a piecewise continuous derivative on 0 to pi. Okay. Now the first part is that the Fourier sine series summation of n from 1 to infinity b sub n sine nx generated by f on 0 pi will converge to, again, 1/2 of f of x minus plus f of x plus at each point of x in the open interval from 0 to pi and to 0 at both endpoint x equal to 0 or pi. Right, so this is the first part. Second part. If f is also continuous on a finite cost interval AB with A, B, okay, so in this case A greater than 0, B less than pi, then the Fourier sine series converge to f uniformly and absolutely. Okay, and absolutely on AB. Okay, so the case that now how about the possibility that A equal to 0 or B equal to pi. So now or, so we will consider both cases in the following two items. So the third item says that if f is also continuous, okay, on A to pi, okay, so in this case B equal to pi, okay, so that f is continuous on A to pi with A greater than 0, less than pi, and if pi equal to 0, then the summation of the Fourier sine series will converges to f, okay, uniformly and absolutely. On A to pi. Now, why this is important? Okay. Look at the Fourier sine series. As you see, when x equal to 0, sine nx n0, so it's 0, right? So this series sum is 0 when x equal to 0. And also, when x equal to pi, sine n pi is also 0. Okay, so the series sum is also 0. Okay, so when x equal to 0 over pi, the Fourier sine series will converge to 0 because it's equal to 0 already there. Okay, and so that to say something about this is the reason why they will at both endpoints, they will go to 0. This is very special. And but for other points, right, in this open interval, okay, it will go to this value according to theorem 11.1.2. Okay, 11.1.2. Okay. So let me construct. So an example is like here, right? So let me use that same example. Pi. Okay. Now to construct an odd function. Okay, so we have now pi here. Okay. And 0, okay, when x equal to 0, and pi, and then minus pi, and then minus f of minus x for 0. The reason we want to have a periodic function, right? So as we know that because it's okay, so for odd function we have that, and so this implies that f is minus pi is equal to minus f0 pi. Okay? But by periodicity, this is equal to minus pi, because f0 pi is equal to, okay, so we should have okay, to construct periodic function, right? So just like here, I just specify only one period, but actually I should say here. Okay. So you see, with oddness, and also with the periodic, so you can see f odd, f sub o minus pi equal to minus f sub o minus pi. So this implies that f sub o minus pi is equal to 0, is equal to f sub o pi. So this is the master to define that when x equal to 0, and also this is implies that f0 equal to minus f0. So this implies f 0 is 0. Okay. So for any other periodic function, at this 3 points, the value must be 0. It must be 0. Okay. And this has been reflected by the Fourier sine series, because when x equals to 0, pi or minus pi, this series converges to 0. Okay, the value of the series is 0. Okay, and so that for odd function. So that the value is here. And we have okay, like that. And okay, like that. And the point here. So we have f of x, and here we have and we have f of r here. Okay. Right. So the first item, for the first item and for all point x in this open interval, this is from the conclusion of the conclusion. And the reason why it's 0 because that for the odd function, so you see that in here the f0 0 minus equal to minus f of 0 plus. Okay, so for the odd function, that the left hand limit at 0, okay, would be the minus. So they have of this sign. Okay, and the right hand limit at 0. Okay, so they have up this sign. You can see here. So this implies that 1/2 of f(o) is 0. Okay. And similarly, f(o) pi minus equal to f(o) pi plus. Okay, and this is equal to yep. So the repeat would be here. Okay. Okay, because this is here. And so this is implies as is also 0. And f0 minus, yeah, I think that would be enough. Okay. So the trigonal metric Fourier series would be the same, right? Generated by f naught on minus pi to pi, converge to 1/2 of f odd. Okay. For each point in, okay, and to 0, I have explained here why they converge, because the average is 0, 0 here. Okay, so when x equal to 0 or pi, then this average is equal to 0. That's why the series, the trigonometric Fourier series, this one, of this other periodic function goes to 0. Okay. Okay, and so the second case is that we cannot exclude the case that f of here. You see that f0 is not equal to 0. F pi, original f pi. This is original f pi is not 0, 2. Okay, so in these two cases, the uniform convergence only good for any finite cost interval which is in this open interval. Okay, when this closed interval is within this open interval. Okay, but if f pi equal to 0, so if f pi equal to 0 here, okay, and f is continuous on a to pi, okay, and f of pi is 0, then uniform convergence and absolute convergence is also good for this closed interval, finite closed interval. Okay. Okay. And the fourth one, okay, I forgot to write down the fourth one here. Or if f is also continuous on 0b with b greater than but less than pi, and f of 0 is 0. Okay, so f of 0 is 0. Then the Fourier sine series converges to f uniformly and absolutely on this finite closed interval from 0 to b. Okay. Any questions? All right, so the last theorem in this section is about possibles theorem. So f is a square integrable complex or real valued function on minus pi to pi, and a0 plus summation from 1 to infinity an cosine nx plus bn sine nx All right, so this one is the trigonometric Fourier series generated by f. Okay. Now, possible theorem says that square plus an plus. Okay. So Bezo's inequality, Bezo's inequality says that this series sum will be less than or equal to this integral. Okay. So Bezo's inequality says that we have this inequality. But the theorem says that inequality is actually equality. Okay. And the proof will be given in section 6. Okay. (11.6) among others. So we will prove a more general theorem. Okay, more general theorem. But so we will deal with such kind of theorem in section 11.6. Okay. So Bezo's inequality actually becomes to equality. So this identity is called Passible's identity. Okay. I'm sorry, I forgot to put absolute sign in the actual notes. Okay. I think the basic reason is because originally I considered only real case, but finally I decided to consider complex case because complex case include real case. And so a lot of notation should be changed. Okay, but but it's too tedious sometimes. Okay, so yeah, so you have to put to do some correction in the lecture notes. Okay, so there because f is in general can be complex valued. So the Fourier coefficients a and bn may be complex numbers. Okay, they may be complex numbers. So that we should put absolute value sign there. Okay. So any questions? So we will prove this identity later in section 11.6. Any questions? Okay, now, so up to now you can see that the trigonometric system, okay, 1 cosine nx, sin nx for n greater than or equal to 1, this trigonometric system is very successful, right? So especially in this section 11.4, we prove best approximation theorem, right? So any partial sum function of the trigonometric Fourier series, right, is the best approximation of the original square integrable function f, because it will minimize the square error, right? Minimize square error. And we also, from the theorem, we see that we have this identity, okay? because this is about the energy. This is about total energy of a signal, okay, in one period. And the total energy actually can be expressed by the serial sum of the square of S value of all Fourier coefficients. Okay, so this is a very, very important result. And in addition, we have several representation theorem about the convergence of trigonometric Fourier series as well as Fourier cosine series, Fourier sine series as well. Okay. So they are so successful. And the next question, do we have other system like a trigonometric system? Okay. And it turns out, so this problem has been dealing with in the mathematical world. And so the success, so we were, so this is called the subject Sturm-Liouville problem. Okay. I have give you a lecture note about 20 pages. So this is a very thick section. Yeah. So as you can see, I can't discuss all the detail of my lecture notes. So I'll give you the essential point and ask you to read the material at home. Okay. All right. And this section is heavily dependent on your knowledge about ordinary differential equations. So I hope you still remember a lot of them. For example, the Legendre differential equation, Basel differential equation, okay, as well as second order differential equations, okay. Right. Good. So now, so my statement is that the success of trigonometric Fourier series expansion of a periodic function suggest us to find other system of orthogonal functions on an interval okay to represent to represent a function to represent functions defined on I. Okay, so right. And it turns out that so we're related to a class of second order homogeneous linear ordinary differential equation. So we consider a homogeneous, okay, second order linear ordinary differential equation of the form. Okay, so it would be fp of x. So it's a function times. So y prime is an unknown function. Okay, and so p of x, p a function times an unknown, the first derivative of the unknown function, and then take the derivative plus q of x plus lambda r of x and y equal to 0. So it's linear. Okay, even though the coefficients are functions, okay, the coefficient of the second order differential equation are functions of x. Okay. Okay. And so on some interval I of the real line, and the interval may be bounded or unbounded. For example, the I, just the whole real line, okay, may be closed or open or half open. Okay, and where we require p of x, q of x, and r of x. So we will consider, this is very important, so I write real valued functions on I. And lambda is a parameter. Okay? So lambda is a parameter and can be regarded as complex number or real number, just arbitrary. But also set function p of x, q of x, and r of x are all real valued. So they are real functions. Okay, they are all functions. All right, so such ODE is called a Sturm-Liouville equation. Okay, so this is called so this is called a Sturm-Liouville equation. Okay, so this is called a Sturm-Liouville equation. Now we will first regularize, so that we will first restrict PQR. Okay. So now, so if P of x and the P prime of x, because that when you take the derivative of the product, you will get P prime x, and the Q of x and R of x. So if these four are real valued continuous function. Okay. On a finite closed interval I equal to AB. And so the first is that we consider a case that the interval I is a finite closed interval, all right? And the P of x, P prime of x, Q of x, and R of x are real valued continuous function, continuity. And we also require that P of x is positive and R of x is also positive for all x in AB. Okay, so if we have these properties, then 11.5, and then the ODE then the Sturm Liouville equation in 11.5.1, right, is called regular. All right, so it's called regular on AB. Okay, so a regular Sturm Liouville equation, all right, it's a Sturm Liouville equations on a finite closed interval such that P of x, P prime of x, Q of x, and R of x are all continuous real value function. Okay, and P of x, R of x are all positive. Okay. Now, but to solve an ODE, we need initial condition or either initial condition or boundary condition. And here we will consider boundary condition. So when together with two boundary condition, okay, so we write down. So there are two parts, K1 YA plus K2 Y prime A equal to 0. So that you can see this is a homogeneous, this is about homogeneous equation on the solution Y and its derivative at point A. And B is L1 YB plus L2 Y prime B equal to 0. Okay. Okay, so we have two boundary conditions, right? At each of the endpoints. Okay, and where the constant K1, K2, L1, L2 are real constants. Okay, so we're talking about real constants. And at least one of K1, K2 not 0, and at least one of L1, L2 not 0. Yeah, because if both of K1 and K2 are 0, then we don't have equation A. Yeah, because if K1 is 0, K2 is 0, then we have 0 equals 0. So there is no condition at all at the endpoint A. So at least the one of K1 and K2 must be non-zero, and at least of one of L1, L2 must be non-zero to avoid trivial condition. All right, so when together with two boundary conditions, all right, then a regular stem Liouville equation in 11.5.1 becomes to a regular stem Liouville problem on AB. Okay, so a stem Liouville problem include so a regular stem Liouville problem include first, a regular stem Liouville equation. Second, two boundary conditions. Okay. Okay. All right. So we'll make an example. Right, so consider a regular stem Liouville problem on 0 to pi. Okay, so we have very simple y double prime plus lambda y equals to 0. And the boundary condition is very simple. Okay. So where we specify A equal to 0, B equal to pi. So the two boundary points are 0 and pi. Now P of x is equal to 1, a constant function. Q of x is 0 function. And the R of x equal to 1, a constant function for all x in 0 pi. And we know K1 is equal to L1 equal to 1, but K2 equal to L2 equal to 0. Okay, so you compare this second order ordinary differential equation with, okay, compare this one, the standard form of a regular stem Liouville equations. It's regular because you see P of x is 1, so they are continuous function, right? And the derivative of P is 0, right? So it's also continuous. Second, P of x positive, right? Because it's 1. R of x is positive for all points x in this finite closed interval. So So it's easy to see this is a regular Sturm-Liouville equation. And these two boundary conditions, right, match to the format we are given there. And so this ODE and these two boundary equations consist of a regular Sturm-Liouville problem. Now, so we will solve this. We'll solve them, and so now first case. We consider lambda to be real, okay? Yeah, because if lambda is not is a complete number, then you can decompose lambda to be real part and imaginary part, and so then you have so basically you are considering ODE which lambda is real, okay? Now, so when lambda is negative, all right? So lambda is a negative number, right? In this case, so a general equation so lambda, okay, you can see is the negative number. So a general solution, yeah, I believe you know how to solve it. So a general solution is y of x equal to C1e nu x plus C2e minus nu x. Okay, so this is why we require nu to be positive, because nu x and minus nu x. Okay, so the general solution has 2 degrees of freedom, right? Because C1 and C2 can be arbitrary. Right? For this regular Sturm-Liouville differential equation. Okay, but when we put the 2 boundary conditions there, okay, because once we put boundary conditions, then we have to then we can solve the problem, right? Now, the 2 boundary conditions, right, implies what? So when we put them, so y is 0, the 2 boundary conditions, all right, so that y is 0 equal to 0 equal to y pi, okay, give us that C1 equal to C2 equal to 0. Why? Well, you can put 0 here. Okay, when you put 0 here, this is C1 plus C2 equal to 0. Okay, so y0 equals 0 means, so this implies that C1 plus C2 equals to 0. And y pi goes, it means that C1 e mu pi plus C2 e minus mu pi equal to 0. And so you can form, okay, 1, 1, and the e pi right here, and this is 0, 0. And you can see that the determinant of this coefficient matrix is non-zero. Okay, so this is invertible. So this is implies that it's the 0 vector. Okay, it's very easy to solve the linear equations. Okay. Okay, so are you currently taking linear algebra this semester? Oh, how about solving metric equations? Not yet? But really? So you are starting from abstract vector space concept. Wow, that's good. That's good. How about in high school? Did you learn how to solve metric equation? Addition, vector addition, metric multiplication. How about Gaussian elimination? Okay, all right. So you can use Gaussian elimination to eliminate. All right. And how about the determinants of a 2x2 matrix? Okay, good. And how about the inverse of a matrix? Okay, good. So you know the property that if, for this one, if the determinant of a 2x2 matrix is non-zero, then this matrix is invertible. You know that? Good. All right, so you can see what the reason why it's zero because this one, because the determinants, you can see the determinant of this matrix. Say this is A matrix, okay? This is equal to minus E mu pi, right? Is that correct? Okay. 1 times this minus 1 times this, right? So this difference. And they are different, right? So that this is non-zero. Okay. So this is implies A inverse exists. All right. So now we multiply A inverse A inverse 0, 0. Okay. So we know A inverse exists. And this is identity. This is identity. C1, C2. And any matrix multiplied with 0 vector is also a 0 vector, right? It's easy. Okay. And identity matrix times a column vector implies C1 the same. Okay. And we solve it, right? Okay. So C1, C2 equals 0. Okay. Wow. If you don't know this, how did you learn to solve system of linear ordinary differential equation? How did you learn to solve them? You must learn how to solve system of linear differential equation, right? In last semester, when you took the ordinary differential equation, you didn't do that. If you have two, for example, you have two differential equations, okay, together, and you have two unknown functions. That is a system of differential equations. No, so you only know how to solve only single ODE. Wow, only so you have two classes, right? But your class. So in your class, the instructor taught you how to solve a system of linear ordinary differential equations. Is correct? No? Oh my God. Really? Oh. Okay, because I taught differential equation many years ago. That is a must to know. Okay, I see. All right, so let me know if you, because I say this section heavily dependent on the knowledge about ordinary differential equations, okay, as well as linear algebra. Okay. So if you don't know any of this concept, I will mention in this section. Let me know, right? And interrupt me immediately. Okay, let me know because this is very important. Okay, so all right, so So the boundary condition give us two linear equations with two unknown, the C1, C2. And so usually we use a matrix equation to solve them by this one. All right. For example, if you use MATLAB, the package, basically you use a matrix to solve them. Okay. And MATLAB is very efficient to handle the matrix manipulations. Right. So that's why a lot of people suggest you to use MATLAB. Okay, but you have to know the basic idea of linear algebra. So that is the case that, okay, so you know when lambda is a negative number, okay, then we have only trivial solution. Means that the only solution is 0 because C1, C2 must be 0, right? So that we have only trivial solution. Okay, for this case. Second, lambda equal to 0. Second case. Now, so a general solution is easy because when lambda is 0, you have y double prime equal to 0. So a general solution will be C1 plus C2x. Okay, so it should be a polynomial of degree at most 1. Okay, so that is, and then the two boundary condition. All right, give us what? So y0, y implies C1 is 0. So y0, so we put 0 here, just disappear. So C1 is 0. And the y pi 0 implies C1 plus C2 pi is 0. But C1 is 0, so C1 pi is 0 implies, C2 pi is 0. Okay. Okay, so first we know from the first boundary condition, we know C1 is 0. And from the second boundary condition, we know that C2 is 0. Okay. All right, so that we have only trivial solution. Okay. Right, now the third case. So the third case, lambda is equal to, lambda is positive. Okay, so let's say nu square with nu greater than 0. Okay, so a general solution, okay, is here y of x equal to a cosine nu x plus b sine nu x. Okay, so we have to resolve to trigonometric the sinusoidal function. Okay. Okay, and all right. So the two boundary condition. Give us, all right, so that first of all, y0, so 0 is equal to y0, and so this is a cosine 0, so cosine 0 it's 1, okay, okay, so cosine 0 plus b sine 0, so that equal to a. Okay, so A must be 0. And how about pi? And so we have A cosine nu pi plus B sine nu pi. Okay, but because A is 0, so this is equal to B sine nu pi. Okay, right? So A is 0, and B there. Okay. Now, so for a non-trivial solution, to have a non-trivial solution means that both of A and B, okay, so either A not equal to 0 or B not equal to 0, right? But A already is 0, so B cannot be 0. We must have B not equal to 0. So that sine nu pi must be 0. Okay, must be 0. And which means that nu is equal to, must be in what? Must be equal to integers. Okay, because nu is positive. So sine nu pi is 0 means nu should be integers. Yeah, etc. Because nu is positive. Okay. Okay. So so that's ynx, which is equal to sine nx, because nu has to be integers, right? So and okay, that's this one x is a non-trivial solution. Okay, it's a non-trivial solution, and for each n in the central number with lambda equal to n squared. Okay, so not every lambda, not every positive lambda has non-trivial solution. Only when lambda is equal to n squared, all right, and n to be any positive integers, then we have a non-trivial solution, which is yn, which is sine nx. Okay, which is sine nx. Okay. Okay, and so we will call this an eigen function of the regular Sturm Liouville problem in suppose here we will call this problem to be, okay, refer in, okay, right? So this function is an eigenfunction, okay? of the regular Sturm Liouville problem. And this one, an eigenvalue of the regular Sturm Liouville problem in 11.5.3. Okay, so such an example, from this example, we find that when we have a regular Sturm Liouville problems, and the lambda is a parameter, then this is a usual case that not every lambda together with, all right, these two boundary conditions has non-trivial solution. Many of them, maybe most of them have only trivial solution, but some spatial value for lambda, all right, for some spatial for lambda, then the regular Sturm Liouville problem has non-trivial solution. Okay, so that's spatial, right? Very, very spatial. And in this case, we find that only lambda equal to n squared, where n is positive integer, all right? We have a non-trivial solution, and the corresponding non-trivial solution is just the sine function, sine nx. Okay, sine nx we have here, right? Okay, and we will continue to say that, okay, with this setting. So if we have a regular Sturm Liouville problem, okay, in this setting, we will show that some spatial lambda, for some spatial lambda, the regular Sturm Liouville problem has non-trivial solution. Okay, has non-trivial solution. Okay, and always exists spatial value of lambda. Okay, we will prove that the fact that this regular Sturm Liouville problem has non-trivial solution, and so we will have eigenfunctions, and we will have the corresponding eigenvalues. Okay, we will have the corresponding eigenvalues. Okay, and from this example, we see the sine function appears as the eigenfunctions. Okay, in such a simple regular Sturm Liouville problems corresponding to spatial eigenvalues lambda. Okay, and we can take the second example. All right, so consider another regular Sturm Liouville problem on real pi, the same. Okay, so we have the same differential equation, but with different boundary condition. This time, we use the derivative of the solution. Okay, instead of the solution y itself. Okay, so we just change the okay, the boundary conditions. So again, we know A equal to 0, B equal to pi, P of x equal to 1, Q of x equal to 0, R of x equal to 1, okay, for all x on 0 pi. Okay, and K1 equal to L1 equal to 0, K2 equal to L2 equal to 1. Okay. All right, so okay, again, 3 cases. Right, when lambda is negative, again, so we have general solution because the ODE, all right, is the same. So we have right here C1. Okay. All right, and so y prime 0 equals 0. So the first boundary condition gives us that new C1, okay, plus minus new C2 equals to 0. Okay. All right. So what is that? The derivative. What is the derivative? This is the new C1, new x minus new C2. Okay. So this is the derivative, right? When you take the derivative, and so the derivative is 0 at the x equal to 0. Give us that. So this is equal to C1 minus C2 is 0. Okay, and the y pi, you give us the new C1 e new pi minus new C2 e minus new pi equals 0. So implies that C1 e new pi minus C2 new pi equals 0. So together we have a matrix equation. Pi, yeah. Okay, and again, you can compute the determinants of this matrix, which is non-zero. Right, so this implies that. Again, so we have a trivial solution only. Okay, so this one has non-zero determinants. Okay, this one has non-zero determinants, and okay, so we have only trivial solution. And the second, num equal to 0. So a general solution. Okay. A general solution would be y of x equal to c1 plus c2x. So this is implies that y prime of x is equal to c2. Okay. And so the condition y prime of 0 equal to 0 implies that C2 is equal to 0. And y prime of pi equal to 0 also implies C2 is 0. Okay. So C2 is 0. And so that we have a non-trivial, okay, so that's y of x equal to 1 is a non-trivial solution. Okay. All right. So that lambda equal to 0 is an eigenvalue of the regular regular stem Liouville problem in 11.5.4. Okay, so lambda 0 is an eigenvalue, and the corresponding eigenfunction is 1. Okay, so we will use this one to be. We say that this is called. I use y0 equal to 1. Okay, it's a non-trivial solution. Okay, third one, when lambda is positive, so a general solution, it's y of x, a cosine nu x plus b sine nu x. So this is implied as y prime of x equal to nu minus nu a sine nu x plus nu b cosine nu x. Okay. And 0 is equal to y prime 0 implies. So when we put 0 there, this is 0. So we have b, nu b cosine. So nu b cosine nu x equal to 0. Okay. Oh, cosine 0. So this is implied as b equal to 0. Because cosine 0 is 1 and the nu is positive, so b must be 0. And implies that now because b is 0, all right, so b is 0. Okay, so we have only, this is 0, so minus nu a, and the sine nu x, nu pi is 0. And so we have that. All right, so to have a non-trivial solution, then because b already must be 0, so a cannot be 0. All right, so to have non-trivial solution, a not equal to 0. Okay, and so that we must have a not equal to 0, so that sine nu pi is 0. So this implies nu is equal to 1, 2, 3, etc. So nu should be positive integers. Okay. Okay, and so a not 0, b is 0, right? So that nu equal to lambda equal to n squared. Okay, it's an eigenvalue, all right, of the stem Liouville problem in 11.4.4. Okay, for all n from 1, 2, 3, etc. And the yn of x, which is cosine nx. Okay, cosine nx because the nu is n, and a not equal to 0. So yn is an eigenfunction of the stem. Okay. Right. So this time, well, we have okay. So that we conclude that lambda equal to n square. Okay. It's an eigen value, okay, of 11.5.4 for all n equal to 0, 1, 2, 3. So I include 0. Why? Because we know when lambda equal to 0, we have non-trivial solutions, and the yn equal to cosine nx. So when n equal to 0, this is just 1. Okay? So when n 0, this is just 1. Okay, so it's an eigen function of for all n, etc. Okay. So now 1 cosine x, cosine 2x, cosine 3x, cosine etc. are eigenfunctions of this regular stem Liouville problem on 0 and pi. Okay, and these two cases corresponding to. So later on, you will see that for any functions defined or any square integrable complex or real value function defined on this interval, we have Fourier sine series expansion by using the eigenfunctions of these regular stem Liouville problems. And for this case, by using the eigenfunctions from these regular stem Liouville problems, then we will have Fourier cosine series expansion for functions defined on the half period from 0 to pi. Okay, and later on we will show similar case for the full trigonometric system. 1 cosine sine cosine 1 cosine x sine x cosine 2x sine 2x cosine 3x sine 3x etc. Okay, but they are corresponding to stem Liouville problem, which is not regular. All right, they are related to, they are periodic. All right, so that, we will show. But first of all, we will consider regular case. Okay, and then we will consider other cases. Okay, so Fourier cosine series expansion and Fourier sine series expansions corresponding to eigenvalues, all right, eigenfunctions, all right, in two different regular stem Liouville problems. Okay. Okay. Now, I will talk about something related to linear algebra. Okay, so we let okay, we know this. This is the set of all complex our real valued square integrable functions f on AB. Okay, i.e., we know that is finite. Okay, so L2 space, and we have known that L2 is a vector space over C. Okay. Now, I believe you know what is a vector space, right? Okay, and so so the addition of two a square integrable functions will be square integrable, right? By by linearity of the integral. And scalar multiplication of a square integrable function is also square integrable. Okay. Okay. Oh. Did I show this before? No? Oh, okay, maybe right. Okay. I have, yeah, okay. I didn't show that. Okay, so first of all, there are some facts for any F and G in the L2 space. Okay, let me show that this is a vector space. Okay. All right, so so we have their product, all right, will be will be less than or equal to right, and the reason is here. This is a number, right, and this is a number. So when we take the square minus sign will be greater than or equal to 0. Is that correct? So this number minus this number, we take the square, will be greater than or equal to 0, right? Okay, and when we expand this product, so this if and only if f of x squared minus 2 will be greater than or equal to 0. Is that correct? And so this says that we